Welcome to Mathematics in the AI Era, a PSC series exploring the mathematical foundations of artificial intelligence. In this episode, we ask a fundamental question: how does AI learn? The answer takes us from error and loss functions to calculus, gradients, optimization, and ultimately, learning. AI systems can produce impressive predictions, but they can also be wrong. Learning therefore requires feedback. The model compares its prediction with the desired answer and measures the difference. This simple idea, prediction, error, correction, is at the heart of machine learning. To make learning mathematical, we need to quantify error. A loss function does exactly that. It assigns a numerical value to the model's mistake. A small loss means a better prediction. A large loss means the model needs to improve. Different problems require different measures of error. We might compare predicted and actual values, or evaluate the probability assigned to the correct answer. Whatever the method, the goal is the same: convert prediction quality into a number that the model can minimize. Imagine every possible set of model parameters as a point on a landscape. The height represents the loss. Some regions have high error, while valleys represent better solutions. Training means navigating this mathematical landscape toward a region where the loss is low. But how can the model know which direction to move? This is where calculus becomes essential. Calculus allows us to study how the loss changes when parameters change. Instead of guessing, the model can mathematically determine how its decisions affect error. For a simple function, the slope tells us whether we are moving uphill or downhill. If the slope is positive, decreasing the parameter may reduce the loss. If it is negative, increasing it may help. The slope therefore provides a direction for improvement. Real AI models have many parameters, so we need more than one slope. The gradient collects the rate of change with respect to every parameter. It points toward the direction of steepest increase in loss. Therefore, moving opposite to the gradient takes us toward lower loss. This idea gives us gradient descent. Starting from the current parameters, the model calculates the gradient and moves in the opposite direction. It then repeats the process. Step by step, the parameters move toward regions of lower loss. Learning happens through repeated small updates. After each step, the model calculates a new loss and adjusts its parameters again. One update may change almost nothing, but millions of such updates can gradually transform a poorly performing model into a powerful one. How large should each step be? The learning rate controls this. If it is too large, the model may overshoot the minimum or become unstable. If it is too small, learning becomes painfully slow. Finding an appropriate step size is therefore crucial. Modern AI models may contain millions or billions of parameters. Their loss landscape therefore exists in extremely high-dimensional space. We cannot visualize all those dimensions, but the mathematics still works. The gradient provides a direction through this enormous parameter space. After a prediction, the error must be traced backward through the network. Backpropagation uses the chain rule of calculus to determine how each parameter contributed to the final error. These gradients then tell the optimizer how each weight should be adjusted. Training modern AI means optimizing enormous numbers of parameters using huge datasets. Computing everything at once is impractical, so methods such as stochastic gradient descent, mini-batches, parallel computing, and learning rate strategies make large-scale optimization possible. The deeper idea is simple: learning is optimization. Define a loss, calculate its gradient, update the parameters, and repeat. Whether AI recognizes images, generates language, understands speech, or learns through rewards, mathematics turns learning into a systematic search for better solutions. We have now seen how mathematics allows AI to learn by minimizing error. But real-world predictions are rarely certain. AI must also represent uncertainty and probabilities. That leads us to Episode 5, Probability: How AI Handles Uncertainty. Like, share, and subscribe to Physical Sciences Consultorium.